All right, 12.7, addition rule for probabilities. Students will be able to find the probability of events that are mutually exclusive and events that are not mutually exclusive. So, what does that word mean? Mutually exclusive. This is when two events have no common outcomes. So let's determine whether these events listed here are mutually exclusive or not. So the first one, a junior winning the election or a female winning the election. Well, couldn't we have a female that's also a junior? And so there are such things as female juniors, and therefore that means these could have the same outcome, and therefore these are not mutually exclusive because they share an outcome, right? There could be female juniors, so we're going to just say not mutually exclusive. Getting a sum of 6 or 7 when you roll 2 dice. Well, there's no way for 6 to equal 7. It will never happen, and therefore we can say that these are mutually exclusive. So I'm just going to write M-E, mutually exclusive. Drawing an ace or a club from a standard deck of cards. Well, if you go back to that first thing in notes, you'll know that there is one card that is both a ace and a club. So that is a shared outcome. We could draw, there's 4 aces and there's 13 clubs, but there's one card that is both an ace and a club. And so that's a shared outcome, so that is not mutually exclusive. So how do we determine probability of mutually exclusive events? Well, if they are mutually exclusive, then it's we simply add those two probabilities together. So if two events A and B are mutually exclusive, then the probability that A or B occurs is the sum of the probabilities of each individual event. Pretty simple. So let's take a look at example 1 here. What's the probability that when a fair 6-sided dice is rolled that you will get a 3 or a 4? Those are mutually exclusive. So we want to do, so the probability of 3 or 4 is simply the probability of 3 plus the probability of 4. That's it. So the probability of 3, well, that's just 1 out of 6. Probability of 4, that's also just 1 out of 6. And 1 6 plus 1 6 makes 2 6, which reduces down to 1/3. So there we go. And that makes sense because 3 and 4 represent a third of the 6 sides of the dice. All right, so practice number 1 here. It says, let's say you're drawing a card from a normal deck of cards. What's the probability that card is a face card? Face cards are jacks, queens, and kings. So there's 3 different ways to get a face card there. Go ahead and just try that out on your own, and then check back when you're ready to check your work. Okay, so the probability of getting a jack or queen or king is the probability of a jack plus the probability of a queen plus the probability of a king. There's 4 of each of those. So that's 4 out of 52, but that reduces to 1/13. So we just do 1/13 plus 1/13 plus 1/13. We already have common denominators, so this is just 3/13. That's all there is to it. It's pretty easy. All right, so now we're going to talk about events that are not mutually exclusive. Remember, this means they do share a common outcome. So if two events A and B are not mutually exclusive, then the probability that A or B occurs is the sum of the probabilities minus the probability that both A and B occur. So now we have to subtract that common outcome. That's what this is. So you might want to say like common outcome, just to remind you that you're going to subtract that. Okay. So Mr. Rose playing poker, and currently he has 4 cards to a straight flush with the cards 5, 6, 7, or 8. So I'm giving you the hard one because we could do it together here. But we got 5, 6, 7, or 8 of hearts. Okay, in poker, this is a really good situation because if I get a 4, it says 1 more card's coming out. If he gets a 4 or a 9, well, then I would have 5 cards in a row. That's called a straight. So that'd be great, right? Because I'd have 5, 6, 7, 8, 9, or 4, 5, 6, 7, 8. That's a straight. And if I get another heart, right, because I have 5, 6, 7, 8. I guess this actually should say or if he gets another heart, he will have a flush because I have 4 hearts right now. If I get 5 hearts, then I have a flush. Both of those are good hands. So it says either of these 2 options are pretty certain to give him the winning hand. What is the probability that he will get a 4 or 9 or a heart? So we have all these different situations. Now, the first thing to realize is that the 4 or 9, that's not mutually exclusive just there, because there's no 4s that are 9s and there's no 9s that are 4s. So that's not mutually exclusive. But 4 or heart or 9 or heart, those are mutually exclusive. So we want to know the probability of a 4 or a 9, or I'm just going to draw the heart symbol, or a heart. Well, that's going to be the probability of getting a 4 plus the probability of getting a 9. Those are mutually exclusive. We don't have to subtract anything. But as soon as we say, let's also account for the probability of getting, that's a heart. Sorry if my hearts are not very pretty. We have to account for the duplicates. So we have to subtract the probability of getting a 4 and a heart. And we also have to subtract the probability of getting a 9 and a heart. Now this looks pretty complicated, but it's actually not that bad because we know how many 4s there are in the deck. There's exactly 4 of them. So we're just going to say, okay, well that's 4 out of how many cards are left in the deck. Remember, I've already taken 4 cards. I know there's 4 cards not in the deck anymore. So normally there's 52, but I have to do 52 minus 4, which is 48. And I could reduce that, but I'm not going to because I'm going to be adding a lot of fractions here, and they're all going to be out of 48 because there's still 48 cards left in the deck for all of these situations. So I'm going to just leave it just like that. So what's the probability of getting a 9? Well, that's also 4 out of 48. Probability of getting a heart now. Well, there's 13 hearts in a deck. So you might think, oh, well, this is 13 out of 48. But remember, the 5, 6, 7, and 8 of hearts, I already have those. So I can't draw these again. They're already in my hand. So we have to remove those from the count. So there's not 13. There's 13 minus 4, which is 9 out of 48. Minus, now there's only one card that is a 4 and a heart, and that's the 4 of hearts. Pretty easy to kind of think about what that one is. So we're going to subtract that one card that is a duplicate or a common outcome. And we're also going to subtract the 9 of hearts because that is the one card that is a 9 and a heart. Okay, and this is pretty easy to calculate. It's going to be out of 48 here. So 4 plus 4 is 8, plus 9 is 17, minus 1 and minus 2 is 15. Now, this may look a little bit tricky to calculate, but it's kind of interesting. You could get a really good estimate of this without a calculator because 48 is really close to 50, and you could just think of this as 15 over 50 for just as an estimation, and you would know, well, all you got to do is double that to get it out of 100, which is your percentage. So it's about a 30% chance that I get one of those cards that helps my hand. But we can just be a little bit more precise here. So let's go ahead. Let's think about how we could reduce this. We could definitely take a 3 out of both of these. Give me a 5. 48 divided by 3. I don't remember. 48 divided by 3 is 16. And so we end up with 5/16. And we can also get a decimal of that, and that's equal to 0.3125. So that's another way of answering that, or we could write that as a percentage. So 3 different ways we could answer that question. But this is a skill that's kind of useful if you ever find yourself playing poker. You might be able to make some predictions about what's likely to happen, you know, in the next card that shows up. You could do some math and figure it out. Okay. What's the probability of rolling a dice that is greater than 2 or even? Greater than 2 or even. So we got 2 situations here. We got greater than 2 and we got even. So probability that the dice is, I'm going to just say greater than 2 or even. Well, that's going to be the probability that it's greater than 2 plus, that's a plus there, the probability that it's even, and then minus all the probability that it is greater than 2. That's my greater than symbol. And even. So this may take a little bit of counting, but remember, for a dice, there's just these 6 sides, 1, 2, 3, 4, and they're just numbered 1, 2, 3, 4, 5, or 6. So the probability that it's greater than 2, well, we can see that it's 3, 4, 5, or 6. There's 4 of them, right? And so I'm just going to put 4 out of 6 here. And the probability that it's even, well, that's 2, 4, or 6. I'll just highlight even there. And so there's 3 of those, so I'm going to say plus 3 out of 6. But now the probability that it is greater than 2 and even, well, greater than 2 and even, that's the 4 and the 6, right? So there's 2 cards there that are greater than 2 and even. So I'm going to subtract the 2 out of 6. And so we see that by asking for something that is greater than 2 or even, we really are really just asking for 3, 4, 5, or 6, and also 2, right? Because 2 is even. It's not greater than 2, but it is even. So really 2, 3, 4, 5, or 6, any one of these would be a success. And there's really just one way to fail. So we'll talk about that in a second. So let's go ahead and do this math. We got 4 plus 3, that's 7, minus 2, that's 5. So we end up with 5, 6. Well, this makes sense because remember we said, you know what? Any one of these numbers is going to be a success, right? And this is the only way you could fail. Well, sometimes if you know, sometimes it's easier to figure out the probability of failing, and then you could just subtract that from 1. So in this situation, if you could recognize, well, the only number that doesn't work is 1, and so therefore the probability of that happening, the probability of failure over success plus failure, that's 1 out of 6. And therefore, the probability of success out of failure would have to be 5 out of 6. So sometimes you could do that too. I mean, we got the same answer either way. I'm just showing you the actual, how to apply the actual formula that we have listed up here. But my point is, sometimes you can think about these things a little critically, and you could calculate the probability of failure instead, and then use that to calculate your probability. So, little trick that you can have. All right, that's it for these notes, guys. I'll see you guys on the next video.